Greetings, welcome. So I think we ended the last video with building this circuit. It's a little different now. I'll explain the extra switches. And then calculating the resonant frequency of an LC tank circuit and talking about how the cap and the inductor behave. And just to kind of reiterate that real quickly, here's a nice little write-up. And the thing that I want to point out is the graph here. So, let's say you charge your cap to 10 volts and then it discharges to 0. At that point, the amp flow in your inductor is now maximal. And so it's as though all the energy that had been stored electrostatically in the cap is now stored magnetically in the electromagnet. But there's no further current there. So the current in your inductor now reverses direction, starts decreasing. Whenever there's a changing magnetic field, there's an inductive spike, for lack of a treatise on it. And because this is going in the opposite direction, it's feeding negative voltage in, so the cap goes down. Now they're showing a completely undamped circuit, which that'd be pretty rare, where this goes all the way down then to negative 10. Now your amperage is 0 in your inductor, and then the cap says, well, I've got all this voltage now, and I can discharge it through the coil. So it starts discharging. This goes up, and it just repeats like that, but these two are 90 degrees out of phase. So that's what I was trying to get across in the last video if I didn't do a good job of it. So in this video, what we're going to do is just do one pulse of a cap through a bitoroidal transformer. Now, I originally was going to pulse, just a cap like this, run it like a flyback, a buck boost, run this, and as a regular kind of transformer, and compare and contrast. I had like 30 minutes, like I haven't even touched this yet, and I'm seeing stuff here that I don't understand. So let's just skip all that, and we'll just pulse the bitoroidal transformer. So here's broken into bits, something that vaguely kind of resembles a bitoroidal transformer. And what it is that you put this here. Here's your primary. You pulse it. It goes out into these two secondaries. And the back EMF from these two secondaries now has two flux paths that it can travel on. It can travel back to the primary, or it can travel in a loop around the secondaries. Now, I say it kind of resembles a bitoroidal transformer because you can see, if we recall, what was his name? I want to say Kishnu Parakaram or something like that, the engineering student who did a write-up on this. And what they did is they used for the primary regular transformer iron with a relative permeability to air of about 200, and then these legs had were made from permeable alloy with a relative permeability of about 10,000. So a great differential, and it would want to flow around the permalloy rather than going back to the regular transformer iron. Now this is all the same stuff, so it's kind of, well, I'm not sure where we should go. And to make matters even worse, look at the mass of this compared to the mass of your legs. That would be an alternate current path, magnetic flux path. So that's bad. Then to make matters even worse, I snapped one of these, and so I had to super glue it back together. And so that puts even more magnetic reluctance in this other path. And that's why I said at the very start of this is a really forgiving approach, because you can actually see what Tom Bearden and Thane Hines and Paracam and many others, I imagine, are talking about, even with this crude an approach. So again, we've got our primary here, and then we have our two secondaries there. So I guess the first thing to do is, while this thing is put together, measure the inductance here so that we know what the resonant frequency is, and then let's get an idea of the Q factor, and then we will pulse it once and see what comes off of the secondaries, and we can see a little bit how this behaves differently. Sorry, I won't have time to go through the regular transformers, but how it behaves differently from a regular transformer or a buck boost. So at a first glance, you might say, when we hooked up the inductance meter here, oh, it's 2.759 millihenries, but no. And this shows what happens when you make a complete circular induction path. It's actually 45 and climbing. So 45, it'll hopefully settle down there. About 45.52. Now, another problem here is, if it goes out like that, and then, that goes down, and it really is sensitive to being lined up just exactly right. Where that becomes a problem is if you're running this thing, say for like 10 seconds at 30 volts, and it's pulsing at its frequency there, it wants to start rattling all over and falling off and whatnot. But that's a whine for another time. But let's try and get this in somewhere. I don't think I'll bother to tape it in, just as we're only doing one pulse. And okay, about 46 point. Stop going up. So on one frequency it reads about 47.45, faster frequency 48.1. So what do we say? Let's say like 47.8, somewhere around there. And I mean, we can mess with the timing once it's in there. 47.8. So if we go to our trusty little spreadsheet resonant frequency calculator that we threw together in the last video, 47.18, 9.625 microfarads. And so the resonant frequency with that cap and coil are 231 hertz, and wave crest to wave crest, that many microseconds. Divide that in two, and that's where this should go most negative. And we can look at that to get an idea of how damp the circuit is. I mean, we want a high Q factor. That would be much better. So first thing, we'll just look at that. But I guess even before that, and when I move this around, it probably changes how that thing's set, and so the inductance could be a little different. But here's our circuit from last time for the most part. And so here, positive and negative, make and break those lines, charge this cap, shut those down. Now you just have your cap sitting there. Everything's all opto-isolated and fine and dandy. And then you put your coil in across there, discharge it across that switch. Again, that's everything that we had last time. Now what's added here is we have a full wave bridge rectifier up here. We have a full wave bridge rectifier down there, and those will be for the two secondary coils. And then I have a switch here and a switch there, and that's just, suppose you want to run it like 50 times, and then you have all this voltage in the secondary that you want to get rid of. So then you just boom, and you discharge the whatever came out in the secondaries. That'll be a little, well, it'll still be useful here, but a little less important since we're only pulsing at one time. But it'll still be, I think, useful here. But first, let's just hook up the primary, make sure everything's running, and get an idea of the Q factor. Okay, so we have our primary going between this leg and this leg of the cap, so that when the switch closes, the cap discharges there. And right now I have the secondaries hooked up to the bridge rectifier, but with nothing across the bridge rectifier, so still unloaded but ready to go. And if we look at our code here, we're just going to do it once. And right now we'll just show it, charging up for 2 seconds just to see that what's in the cap when it's charged, and then the switch shuts off and then goes for on time high. Now our calculated on time for most negative was or is 2,164 microseconds. But I've been moving this thing all around here, and you saw how sensitive it is to where these two things are set with each other. So it's not clear if it's, you know, exactly the same as what I put for the measured induction. But that's the idea, is we'll just first look at how this thing is doing and making sure that it's discharging and getting an idea of the Q factor. So as Admiral Ramius said in the Hunt for Red October, "Give me a ping, Biddly. One ping only, please." I was trying to do Sean Connery. That sucked. So the first thing we can see, we're charging up to 10 volts, and then it's flipping negative to negative 8.43, and that's a 10 UF cap. That's really not bad. It might even be a bit better because, as I said, it's got moved around, so the inductance reading is probably off. I'm just going to fish around a little bit, and what do we want to do better than? Better than negative 8.46. Okay, I don't want to spend all night on this, but I'd fiddle around a little, 2,410 microseconds. And we go from 10.01 to almost negative 9. So this is, I would say this is a fairly undamped circuit, and it's got a pretty good Q factor. So now I've hooked up the first secondary, and here's sort of the beginning of the strangeness. So now this goes from 10 to negative 6.73 instead of 10 to negative 9. And out here we're getting 4.4. That's what it looks like to me. Let's see again, 4.43. Now, the oscillation here is sort of being preserved. And they would talk about that as being, powered by reactive power if this was like an AC transformer. But what I'm getting at there is that that's not going to zero, or this is not zero while this thing is negative. And that's different than like a buck boost or a regular transformer. Now, it's not great at all. I think if this thing were built right, maybe it would go negative 9 to, negative 8.8 or something like that, 8.9. It wouldn't be much deformed at all. But you can already see something. Now what we're going to do is add in the other secondary. Okay, I made such a big deal of it, and it didn't work this time. Oh well. But now we put in the other secondary, and I think it was going to about 6.8 before. Now it's going down to about 6.5. This should be higher than 4.4, but it's lower. I don't know why that happens. And we have another secondary here. It's only putting out about 2.1 volts. I may know why it's not why it's happening, but let me think about that. The reason it's putting out 2.1 volts is because I cracked one of these legs, and so the flux path to one side is, just real smooth, and the other side is not good at all. These things, I've measured the inductance, they're fairly similar, but this one's like twice as good. That's why I'm saying it's a very forgiving approach. But what you can see is even with two of these, there's still that oscillation, even though it's been deformed somewhat. And again, this thing is like a horrible setup for that, but you can still see what's going on, is that you're still getting the oscillation. I just find that remarkable. That's why I'm remarking on it. All right, I'm sorry. Don't know why that didn't work. But what you were supposed to see was that when this one was attached, the voltage was higher here and then higher here. It didn't happen. When I just, flat out run this thing and then put, say, like a 1K ohm resistor across here and 1K ohm resistor across there, you will see that when this is loaded, that more voltage comes out here. And likewise, if this one's not connected, then less, less power out here. So it is there. I don't know why that really didn't work that well in this iteration. Now, it's also when I was, just running the thing and measuring volts amps in, volts amps out here, volts amps out there, with a 1K ohm resistor. Didn't really work with the 100 ohm. You get too much deformation of the LC tank circuit with this, just ridiculous sort of setup. But as I said, it's very forgiving. With the 1K ohm, yeah, I was seeing the same stuff that I want to say Kishnu was talking about, and that others have talked about, that Kishnu documented. And to wrap this one up, I mean, I will say that I didn't initially see it. At like 5 volts, it was 60% efficient, and then 80%, and then 90, and then at 30 volts, it was like 95% efficient. So then I went to 40 volts, and suddenly it went down to like 80% efficient. And I was like, you've got to be kidding me, no. And so I kept running it, and then one of the channels fried. And then I remembered this thing is swinging then from like, 40 to close to negative 40, say 40 to negative 30 or something like that. We saw that it was fairly high Q factor. These are 60 volt Comus AC37. So you can't just think about the positive that, you're 40 to 0. No, 40 to negative 30 is 70. And so you're frying it. And that's why it stopped getting better. That's why you blew up the channel. I've done that so many times now. It's like what Loki said to his brother Thor. Are you ever not going to fall for that? That's about what I feel. But so I have some 200 volts alternating current things that have actually arrived. So, then I can go up to 50 volts. But that wasn't where I saw, Kishnu's delight. The way I got this thing going over unity with the 1K ohm resistor on each of these at 30 volts and even under 30 volts, it was over unity down to 20. In what I'm going to be a braggart. What has to be the greatest MacGyver of all time, or it's at least a good MacGyver. Boom. Once I put that there, then it was over unity at 20 volts. And if you understand what I've been talking about, then you understand why that happened. And once I saw that, then I've been just reading assiduously on transformers, and I can't make heads or tails of it. I mean, it's so complicated. I can't tell whether they're talking nonsense. And then all of the parameters on the data sheets, they have like initial permeability, relative permeability, reference permeability, effective permeability, permeability. Yeah, I made up the last one. But I mean, it is a complicated zoo, and that's just talking about permeability, and how much of it is just the manufacturers talking different language, how much of it is actual fundamental or whatever. But again, once this piece of tape was on there, then the thing was over unity. That's all you needed. Sorry, but true. With a 1K ohm. Now, again, with 100 ohm, you can't do it because you still got too much deformation. But they have air-gapped E-cores, and they do have the parameters on there. I think I'm starting to understand some of what I'm seeing with parameters. It is. I mean, this ain't my area. It's real complicated. But like from what I can gather, there's an E-core, say with a 1 millimeter gap, and so the permeability is 100 there, and then the material itself has a permeability of say like 1500. So that's maybe not as good as the write-up that was mentioned in the video a few times ago with permeability 200 and then 10,000 on the legs around there. that might be kind of overkill. And, you know, it was 15 bucks for an air gap core. So 100 and 1,000. And when you decrease the permeability here, you're sacrificing some of the Q factor, you know, depending on how much wire you can get on there, which, you know, you're space constrained. So you're sacrificing some of the Q factor, but you're improving what's happening here. And I apologize again, mea culpa, mea culpa, mea culpa, that I couldn't show it. But what you'll see when this is set up in the next one is that when it's loaded, it's benefiting, the back EMF is benefiting the other one. So the more of it that you can get to not go into here and to go around to there, and again, look at how horrible this is in terms of, you know, the area there, it's all the same material. Shouldn't have worked at all, but it does work. But it's sort of a strange time. I don't know how you pronounce his name, but Oersted or whatever, but, you know, one of the luminaries or whatever. And, you know, when he saw that a compass needle got deflected by a current, I mean, he immediately wrote that up and just sent it to all of the scientific centers of Europe. And similarly, when Faraday first observed induction, immediately just got that out. And I think sort of the difference is, you know, back in that time, you know, they had like the Royal Society, and who was it, like Francis Boyle, that did all the you know, the ideal gas laws and things like that. And I think it was sort of like they were court jesters, you know. It was sort of like, you know, well, you know, Mr. Boyle has taken the air out of the air and you can't see anything. These jolly odd fellows. What will they come up with next? And over time, you know, it went from there to, you know, like the Wright brothers, and then fighter planes, and then atom bombs, and so on and so forth. So it kind of becomes like, well, you know, just keep your mouth shut. Because it's no longer a novelty kind of comedy routine for people that that like to, as people that like to govern. You know, I mean, might as well mention it. And again, other people may see different when they do the work. Okay, so that's it for now, and in the next video we'll run the thing and have fun with that. And stay healthy, everyone. Thanks for watching. Ciao for now. Bye-bye.